Alright, let's do what turns out to be a fairly quick problem. By the way, I'm trying some new things in terms of like positioning and writing, so I apologize if my writing ends up being a little sloppy or something. If anything, it should be a little better, but I think this position will be better for my wrist and not cause my wrist to like explode. Not like the way my computer does where it heats up, but in the way where it like gets cramps and then you can't do wrist things. And that's bad because I like my wrists. So, anyways, um, so we have another localization problem, and we have prime ideals. And what I'm starting to realize is with these problems is you want to look at the important ideals of a ring. And what are the most important ideals? You've got maximal ideals, which are prime, and we've also got annihilators. And these are both types of ideals that are useful, and they're both going to come up in this problem. And so typically when I was first looking at this, I was a little stuck because I was like, oh, so for every prime ideal P, then this holds like the second part of the if and only if statement says for every prime ideal P, and so that makes me think, oh, I have to be considered like take an arbitrary prime ideal P, something like there should be some way that you use all prime ideals. And I think, let's see, I did look this up a little bit. I think there are ways where you can use every prime ideal. Like you take an element from R set minus every prime ideal, and you do something with these. But this particular solution is only going to focus on important ideals. So let's start. So if m equals 0, then clearly MP equals 0 for every prime ideal P. Alright, and so that finishes that direction, and I'll leave the second direction to you. Just kidding. That's something that I would say if I were like a lecturer and wanted to be mean. But anyways, for the other direction, we're going to assume for contradiction that there exists some element m in capital M set minus 0. Okay? Now consider the annihilator of this element m. And of course the annihilator, this is just the collection of all, here let's do little r in capital R, such that Rm equals 0. This is a proper ideal of R. And why is that? That's because, well, you can check that it's an ideal, but the annihilator, this is a very important ideal in ring theory. Well, I guess this is more module theory because we're thinking about things acting on our set. And so, but it ends up being an ideal of the ring that's acting on our group. So it's an ideal, and then it's proper. Why is it proper? Well, let's see here. Rings contain 1, right? This is a they even say that R is a commutative ring with 1. So now if you apply 1 to M, then you just get M, and we have assumed that M is non-zero, and therefore 1 is an element of R which is not in the annihilator of M, and thus annihilator of M is a proper ideal of R. And thus it's a proper ideal, and thus is contained in a maximal. You know, I'm gonna switch chairs really quick. I have like a really high chair, and I was like, oh, maybe that will like help with posture and stuff, but it's not. So I'm going back to my lower chair. The main thing is I need to work on like not like resting my wrist on the table. Like, you actually want your hand to be like floating above the table and stuff, and that makes handwriting harder, and so that's why everything looks sloppy. So in a maximal ideal P of R, and I'm just going to add parenthetically here, this is by the axiom of choice. That's how we needed the axiom of choice to prove the existence of maximal ideals. The fact that every ring has a maximal ideal. Now, maximal ideals are prime, and that's a basic fact about maximal ideals. It's not a very difficult proof. You should go back and review that proof if you don't know it off the top of your head, because it's pretty important in ring theory. Maximal ideals are prime, so P is prime. By assumption, MP is 0, and so in MP we have M over 1 equals 0. But what does that mean? It means M is equivalent to 0 over 1 in MP, i.e. there is some element S. We'll call it S, and it's going to be in R set minus P, because remember, R set minus P is what we're using as our multiplicatively closed set S that we use in our localization S inverse R. So anyways, there's some S in R set minus P, such that SM equals 0. And so S is in... Here, let's make that part of the same sentence. And so, S is in the annihilator of M, which is a subset of P. This contradicts the fact that S is in R mod P, because that means that S is not in P. So we have that S is in P and it's not in P. And of course, the P here, P does not equal NP. No, I don't know. I was trying to do a P equals NP joke there, but it just did not. It did not happen. So I'm just gonna kind of end this as quickly as possible so that I can get over that failed joke attempt. So this contradicts R set minus the S is in R set minus P, and hence M is 0. And so there we go. This completes our proof.